Dear students, in this video lecture, I want to teach you how these gates are implemented in reality. Okay, in actual silicon. So we are having different types of gates, NAND gate, OR gate, etc., etc. But actually, they are all implemented by transistors. Okay, so now this logic gates. Now, if I take an AND operation, this is a logical operation. We say that A dot B. Okay, so now this A and you are having a logical operation here, but actually how they are implemented? They are implemented using transistors. So this transistors may be BJT, that is bipolar junction transistor, or it may be CMOS, and there are many other families also. We call these things as families. Okay, so T transistor logic. We call this BJT based circuit as transistor logic, and then the MOSFET base, all these things you would have studied in your first year. So MOSFET based devices as CMOS devices. So in a CMOS device, you will be having an NMOS transistor and a PMOS transistor. They will be seen in pairs. Okay, you will have all these things in pairs. For every NMOS, there will be a PMOS transistor. This is MOS is what is it? A metal oxide semiconductor FET. Okay, it is actually a MOSFET. Okay, it is a FET is a transistor. You already know that. So if it is a N channel one, you call it as N MOSFET, and if it is a P channel, you call it as P MOSFET. Okay, so now using these two, this current logic family is the CMOS, which is very commonly used is the CMOS logic. So we are going to see the CMOS logic now. Okay, so what is this? This is a gate. Okay, this is the gate level circuit, but inside that you are having a transistor level circuit. Okay, so very quickly we'll see how these gates, basic gates, and some Boolean expressions are expressed using or implemented in CMOS logic. Okay, so now for that you need to know the NMOS operation, NMOS structure. So NMOS will, the structure is like this. You would have already studied. So there are two diffusion layers, N plus diffusion layer, and there will be a channel formed between these two. This is called as source and this is called as drain. There will be a channel formed between this source and drain. Okay, with proper biasing, proper voltaging. Okay, so there is another terminal called as gate. So this gate is the control device, control terminal. Okay, so from N to so from source to drain, there will be a current flowing depending on the voltage you are giving to gate. Okay, so the gate will be working as the controlling voltage. Okay, so it will have a p type substrate and then two n plus diffusion layers, and there will be a SiO2 layer, and then a polysilicon or what is it, metal, similar to metal layer. You will have a polysilicon layer, and then the gate will be there. Okay, so now when the transistor is off, there will be no current. It is in the off position, and when you properly bias this, and if the gate is positive, okay, if the gate is having a voltage which is more than a threshold voltage, there will be current flowing through this. This is the operation of this. Okay, so this there will be, excuse me, there will be current flowing through this when this gate is positive. So NMOS operation, a channel is formed when gate is given a positive voltage. So gate is positive, and then you will be having a what is it, current flowing through the transistor. Okay, similarly the PMOS transistor will work on the opposite way. So when the gate is low, a transistor is on, that is the P type MOSFET transistor will be on when the gate is given a low voltage. So you need not recall all the operation and all. You need to remember how it is working as a switch. Okay, so in a P transistor you will have two P type diffusion layers, and a channel is formed when this gate is given a negative voltage or a low voltage. Okay, so this is the symbol. Okay, this is the symbol for PMOS, and here is the symbol for NMOS. Okay, so so this is the gate terminal, drain and source can be exchanged. and if you're having a bubble over here, that means it is a PMOS transistor. Okay, so now you have a NMOS transistor and PMOS transistor. This is the symbol. This is what you will use. Okay, so now the transistor has switches. So NMOS transistor will be, when gate is 0, it will be off. Okay, there will be an open circuit between the drain and source. If gate is 1, there will be a closed circuit, that means it is on. Similarly, just the opposite for a PMOS transistor. So this slide is very, very important. You need to remember this. Okay, so CMOS circuit, NMOS transistor is on or it conducts when the gate signal is 1. Okay, logical 1. That means logically you are giving a voltage of 1. It may be 5 volts or 3 volts. You are giving a positive supply to that. And then PMOS transistor will be on if gate is given a 0 voltage. Okay, here 0 logic, and then it will be off. It will be open circuit when gate is given a 1. So they are operate just in the opposite way. Okay, and you put them together and call it as a CMOS circuit. Okay, so now same thing, MOS transistor as switches, same diagram. Now there is one advantage of combining these two, because NMOS transistor gives a good 0 and then PMOS transistor gives a good 1. So you are combining both and to get a good logic voltage levels. Okay, you may not understand this, leave it. Okay, so the signal strength, you may be having a signal strength of you may be using a VDD of 5 volts, or you may be using a VDD of 3 volts, depending on the technology node. Okay, so it may be 5 volts or 3 volts or 2 volts or 2.2 volts or 1.8 volts. So that will be called as the positive VDD voltage level, and then 0 will be the 0 voltage level. Okay, now we'll come to CMOS inverter. So this NOT gate. Okay, NOT gate is called as inverter, and this is the symbol. So you are giving A as the input and Y as the output. So if you understand the working of this, you can easily do all the other gates. Okay, so the inverter, and the circuit needs for how many inputs are there, that into 2 number of transistors. See, if there is only one input to the gate, you will be having one NMOS transistor and one PMOS transistor, and the NMOS transistor will always be in the lower side and it will be connected to the ground, and the PMOS transistor will be drawn on the upper side. Okay, upper portion of your circuit, and it will be connected to VDD. Okay, so now here you have one PMOS transistor and one NMOS transistor, and the gate of both the P and N should be connected together, and the input should be given over here. Okay, so this is the connection. So there is a series connection here, and this output is taken at the middle point. Okay, sorry. Okay, so now imagine that A is 0. So you are giving a 0 here. So this is connected to the gate of both the transistors, to the NMOS transistor and also to the PMOS transistor. So if gate voltage is 0, your PMOS will conduct. Okay, this will be on and this will be off. Okay, so as A is 0, okay, so if I am giving A is 0, this will be on. Okay, this transistor will be on and this transistor will be off. Okay, so now if this transistor is on, that means this is conducting. Okay, so now this voltage level will be coming to Y. So Y will be equal to VDD. So this will be equal to logic 1. So if you are giving 0 as the input, you will be getting Y1 as the output. Similarly, if you are giving A is 0, sorry 1, then this will be on. Okay, your NMOS transistor, this is transistor will be on and this will be off. Okay, so if this is on, then it will be connected to the ground, which will be equal to 0 volt. So if A is 1, this transistor, the lower part of the transistor is on, circuit is on. So it will be pulled down to 0 voltage. Okay, so this is your, this output is 0. Okay, where is it? This output is 0. So we call this as pull up path. Okay, pull up. Okay, so the voltage is pulled up, pull up path, and this is pull down path. Okay, now for a 2 input NAND gate, so I'll draw it here, then we will be 2 input NAND. Okay, so you have this. So here you have AP A dot B the whole bar. This logic is very comfortable for a whole bar. Okay, if there is a whole bar in the circuit, it can be directly implemented, and then every AND operation, okay, ANDing operation will be converted to series connection. OR operation will be okay. So OR operation will be converted to parallel connection. Okay, so now here if there are two inputs, you will need 2 into 2 4 transistors together. Okay, 2 NMOS transistor and 2 PMOS transistor. So now for the NMOS that is pull down circuit, you will have 2 transistors in series, A and B in series. Okay, and the pull down should be always connected to ground. And if the NMOS circuit, okay, this is the N network, we call this as the N network. So this N network, if you are having a series connection, here you convert it into a parallel connection. Okay, so you just draw the ulta. If it is parallel, you make it series. If it is series, you make it parallel. Okay, so now this A and B are in series here, so make them parallel here. Okay, and then make them parallel means the ends of these two are connected, and these two ends are also connected, and this should be connected to VDD. Okay, and connect these two networks, and at the middle take your output Y. Okay, so right now you see it here. Okay, I drew it slantingly. Here it is, right? Okay, so now for 2 input and NAND gate, there should be a whole bar. So NAND is having a whole bar, A dot B the whole bar, and A and B will be connected in a series in the N network. Okay, so this is called as the pull down tree or pull down network. This is called as the pull down network, and this is called as the pull up network. Okay, so pull up network is made of P transistors, pull down is made of N transistors. So these two are uh, so these two are connected in series, and here in the P network, these two are connected in parallel. So connect them and again connect the N network and P network, and at the middle take the output. Okay, so this is the NAND implementation using CMOS. Similarly, we'll see, okay, inverter we have already seen, NAND gate we have already, okay. So we'll see the operation of the NAND gate. So now NAND gate, you have 4 combinations. So A is 0, B is 0. Okay. So now if A is 0, B is 0, these two will not will be off, and these two will be on. Okay. So if both are on, if any one of them are on, you will be having a VDD here, and that comes to Y. So the higher voltage comes here to Y. Okay. So if both are 0, okay, I am having a 1 over here. Now A is 0 and B is 1, so that means here this A transistor is on, and then here the B transistor is on. Okay, so here they are in series. So only if both are on, you will be getting a 0. Otherwise, here any one of them is on, here you will be getting a 1 over here. So this is also 1 and so on. So you will have, yeah, here it is explained. And so both are, the upper both gates are on, okay, and these two are off, so you are getting a 1. And in the next case, this is on and this is off. Here one is off and one is on. Okay, so this path is closed, but this path is open. What is it? It is connected. Okay, so this VDD will come over here, so you will get a 1. And then the next case, this is on and this is off. Here one of them is off, so it will not be connected to the ground, but it will be connected to the VDD through this transistor, A transistor. So again the output is 1. Okay, in the next case, both the P transistor is off and both the N transistor is on, so this 0 voltage level will be coming to the output, so you will be getting a 0 over here. Okay, so this is how these logic gates are working. Similarly, NOR gate. So NOR gate, you will be having just the opposite, that is your NMOS structure will be having transistors in parallel, and PMOS will be having transistors in a series. Okay, so now you will be having, you can be, if 0 0, both these transistors are on, so you will get a 1. Okay, and for 0 1, only one of them is on, so you will not get it. But here any one of them is on means you will be getting a 0 over here. So for all the other 3 cases, you will be getting a 0. So if you understand which transistor is on, which is whether NMOS is on for a what is it, input gate voltage, or PMOS is on, you will be able to draw the circuit. Okay, 3 input NAND gate, you will be having 3 transistors in series in the N network, and then 3 transistors in parallel for the P network. Okay, and then for compound gate, okay, this is a complex gate. So what is the function which is, okay, so first we'll implement this and then we'll go to this. So now what is given is AB plus BC plus CA, the whole bar. Okay, so now I will implement this AB plus BC plus C. Okay, so I'll teach this, listen carefully to this. Okay, so you are given a complex function AB plus BC plus CA. Okay, so now there is no bar, so you are using a bar over here. Okay, and it is AB plus BC plus CA, the whole bar. So only if the whole bar is there, you can easily use this procedure. Okay, finally you will have an inverter. So now there are 3 what is it, AND operations here. So all these 3 AND operations, and then you are having in between OR operations. Okay, so we'll need more space. So I'll so first AB, so AB will be 2 transistors, 2 NMOS transistors in series. Okay, so A and B, and then there is a plus symbol here. Okay, plus symbol here, right? So there is a plus symbol here. So this, for this plus symbol, you need an OR operation, that is you have to put a parallel one in this, but BC will be 2 transistors in series. Okay, so I will again have a series, 2 transistors in series, so BC. Okay, again I'll have 2 more transistors, so A C or anything. Okay, so now you have implemented three AND terms, and they are all in parallel, so you have to connect all these things, all these upper lines. Okay, so this is one path, this is one path, this is one path, connect all these things, and the what is it, bottom line to ground. Okay, connect it to ground, and then you just draw the ulta of this. So now if these two are in series, here they will be in parallel. Okay, so now these two will be in parallel, that is you will have 8, there should be a bubble, and here also there should be a bubble. So this is A and this is B, okay, and then in series, here they are in parallel now, so here it will become, these two will be in parallel, but it will be in series with A and A B, okay. So now again I'll have okay, BC, okay, and then CA, okay. So now all these things, whatever you have drawn here in series, we have drawn in parallel here. Whatever we have put in parallel, we have put it in series here. Now connect these two networks. This is your, this full thing is your P network. This full thing is your N network, okay. So P network should be connected to VDD, okay. N network should be connected to ground, okay. So in between you will have your Y. So now this is Y, or this is equal to F bar, okay. So you, what you can do is, we can again have an inverter to have get F, okay. So now this can be again inverted. So this is a PMOS and ground and VDD, okay. So here you will be getting F, because here you got F bar, so again I am inverting. See, if the function is already given with complement, okay, suppose if the function is given us with complement, suppose if I am having FH, okay, so if I am having H is equal to AB plus B, same function with complement, I do not need this part, okay, this part is not required. Here itself I will get the function H, okay, hope you understand. So if there is a whole bar, there is no need of doing anything, an extra inverter is not required. If there is what is it, no inversion for the whole function, then you have to invert it, okay. So this is yeah, this is, you will be having similar problems, okay. So how to implement a complex logic function. So some whatever may be the anthem, you will be having all the anthem connected in series in the NMOS what is it, N network, okay. So this network is called as N network, that is a network of N transistors, and this is called as P network, okay, that is PMOS transistors, okay. So PMOS transistors, it will be on the top, it will be connected to VDD, and at the bottom it will be connected to ground, okay, and in the middle you have to take your output, okay. So simple, similar questions only will be given. So AC plus BD, okay, it is simple. You will be having two same question with one term less, okay. So these are your N transistors. So how many ever inputs you are having, those many number of transistors you will have, okay. Now this is one term implemented, this is another term implemented, connect them in parallel, and at the bottom you give it to ground, okay, and just put it in the other way here, okay. So connect it in parallel here, put a bubble here, so AC, okay. Similarly you have one more connection, P D, okay, connect these two networks, this network and this network. In between you will take output, and then at the top you will be connecting it to the power supply VDD, bottom you will be connected to the ground. So it will be like this, okay. You have a P network and you have a N network, the N network together it is connected to ground, Okay, and this is connected to VDD power supply, and then in the middle you will have your output Y. Okay, so you can see this slides, and you can what is it, if you have any doubts you message me. Okay.